Hello, I'm Dulanjana Pereira, and I'm here to present my final project on autonomous vehicle overtaking system. Autonomous vehicles has become a real thing. There are autonomous vehicles available in the market for the public. However, there are some limitations that deliberately imposed to ensure the safety of the human because there are some things that we still haven't figured it out properly to make sure that it works 100%. When a vehicle goes in a high speed, it tends to be unstable. For example, when you overtake a vehicle, you increase your speed and it can lead to a catastrophic destruction if you make some small mistake. As well as when you overtake, you have to consider the incoming traffic, as well as you have to predict some level of what will then front vehicle will do. So if you want to automate this process, you have to have a controller that can predict a future as well as robust for different unseen scenarios. So in this project, I'm going to use a model predictive controller to derive a vehicle overtaking system. So I formulate the problem in a simpler fashion to understand the MPC control and apply this MPC control on this problem to uh, overcome the prevailing problems. So in this system, I assume my traffic is dynamic. It goes here and forward and backward. However, it doesn't change the lane suddenly. There's no abrupt changes or movement in the system. As well as I don't give a path to the system, only this goal state. Controller decide which path, which trajectory it should, best trajectory that it should take to go through the system. So, and also I'll demonstrate different scenarios to show how robust my system is. And so before going to the model predictive controller, let me talk about a little bit about the first step of the autonomous navigation, the path planner. So if you have a controller that do path planning and controlling both at the same time, then yeah, model predictive is some one kind of controller, but there are the controllers that only control the vehicle. You have to provide the path separately to the controller. So there are like standard, like very widely used path planners like Dijkstra and Astra, which are optimal path planners. It searches through entire space and provides you the best path, but very inefficient. It takes a lot of time to compute the path. Then visibility roadmaps and RRT are useful real-time path planners for obstacle avoidance, especially. They consider the obstacle and plan the path, but they are not optimal path. It can be suboptimal paths. So other than these standard algorithms, there are like optimization algorithms like genetic particle sum optimization and colony approaches to figure out the best path for a given condition. Then artificial potential field, widely used in autonomous industry, autonomous navigation field. It create this artificial potential field hills, and that actually drives away from this hill. Actually the vehicle drives away from these hills. It basically keep the vehicle on this flat terrains. And then neural network and reinforcement learning, other machine learning algorithms. There are like a lot of algorithms, machine learning algorithms for develop a path planner. So basically, they approximate the environment and the best path. So then now I'm going to talk about some controllers. In this project, I consider 8 autonomous vehicle controllers for autonomous navigation. So PID is the first one anyone should talk about because it's very easy to understand, easy to implement, and also it's real-time controller. But it only suitable for linear systems. It has a difficulty in controlling nonlinear systems, and it's also not very robust. It can't handle high noise, but you can modify the PID controller to handle noise. It's kind of very powerful, but not for a complex and highly nonlinear systems. PA Pursuit is the oldest version of a vehicle control. It's mainly used for uh, uh, missile controlling. It basically gives you very smooth path to towards the trajectory. So if you are away from the trajectory, look ahead from the vehicle to the trajectory and drive the vehicle towards the trajectory in a smooth fashion. So real-time controller is very fast, and you can make it robust if you define the path and the system well. However, it has very difficulty when hard corner, for example, 90-degree corner or more than 90-degree corners, it's very difficult to take the vehicle towards that path. And it's not good for a dynamic environments. Stanley is the, I would say, development next version of peer pursuit. It actually look for the perpendicular distance from the vehicle to the trajectory, the reference trajectory, and try to minimize that error as well. So it's a very fast controller like peer pursuit and can handle complex shapes like this 90-degree angle corners. And it's same as peer pursuit, relatively simple, but also suffers from dynamic environment. LQR, LQG is another optimal controllers. It analytically calculates the optimum uh, input to the system using linear transformation, linear matrices, linear transition matrices. So it's widely used for trajectory tracking, for example, lateral control of a vehicle, basically lane changing and stuff. And it's very computationally efficient because it uses matrices to calculate analytically the optimum solution. As I mentioned, it needs a linear transition, so it's limited to non-linear systems. You can modify it for non-linear systems, but it's not. You need to have very good, accurate, linearized model of the system. Otherwise, it tends to give you unstable outputs. So value iteration is actually basis for linear code, LQR, linear coded regulators, and Gaussian, and it is also optimal. Value iteration is also optimal controller and easy to formulate. You only need to set up the states and the value function. If you want continuous value function for continuous space, you can have neural network or something, and everything else you can use a table for value iteration as a policy. It actually gives you policy. It says, okay, if you're in this state, this is the best action you should take to go to this direction. And there are a couple of other like finite horizon and infinite horizon value iteration systems. And this is computation very inefficient. It takes a long time to compute because it look for all the possible states and so possible actions and find out the best one. So next come very famous controller feedback linearization, which is used in a lot of systems, highly complex nonlinear dynamic systems can be controlled by feedback linearization, especially soft robotics, deformable robots, and other complex industrial plants. But it needs accurate dynamic model, which is very difficult to model. If you have a dynamic model without uncertainties included or any other stochastic nature of the system, then it tends to unstable and gives you weird results. So next come the star of the presentation, MPC. In my case, I use nonlinear MPC. It basically, as I mentioned, it looks a few steps ahead and figure out which action that minimize the future steps cost as well, future step cost. So you always try to go towards the goal location or the reference trajectory. So it can handle dynamic system because it do this calculation every single time step, every single step. So if the environment change in the next step, it can change the current input or the next input according to the next change environment. And I am demonstrating one kind of situation in my research section. So it's not limited to linear system. You can have any nonlinear systems, but when the system is very complex, it takes a lot of time to compute. In my case, mine is a very simple one, so it only takes like 0.01. That means 10 microseconds to calculate one step. So also it very sensitive to model if you have an inaccurate model because model predictive controller use the system model to predict the future. If you have a inaccurate model that gives you a wrong prediction and leads you to catastrophic disaster. Machine learning is basically used for almost everything, everywhere. So you can have a machine learning based controller, for example, neural network, as I mentioned in value iteration, you can plug a neural network there. And reinforcement learning is widely used controller. Uh, it is very robust and you can have it for any system, linear, nonlinear, very complex. It basically approximates the system and approximate the controller and the environment so that it can generalize the system and can do something when the unforeseen uh, dynamics or uh, scenarios occurred in the system during the operation. However, it required a huge training, huge data set, and if you have provide a wrong data set and wrong parameters, it gives you a wrong controller that is unstable and not robust enough for a different scenario. Now I'm going to talk about my system. So here I consider my four wheel as a bicycle. It collapsed two wheels together, and as you can see, it's basically a bicycle shape, and this delta is the steering angle, one of the input, and psi is the heading angle, one of the state, and v is the velocity, and x and y is the global position of the vehicle. In this case, I consider the point of interest or the center of gravity of the vehicle as a rear wheel so that I can eliminate um, uh, uh, the beta, the slip angle. The reason I eliminate the beta because it gives me a hard time when I derive the Jacobian. I used a Jacobian for this state space uh, to improve the optimization speed, the accuracy. So it gave me some difficulty when deriving that one and ill conditions. Therefore, I decided to keep it center of gravity here to eliminate the beta angle. So L is the length of the vehicle, which is 3.5, and this is my continuous state space. Nonlinear model predictive control in MATLAB. That tool is basically a discrete tool. We use for loop to calculate. So that I thought, okay, discrete version will be a very good and easy way to implement my system inside the MATLAB because I implement all my functions and stuff in MATLAB, and I developed my own simulation environment to simulate the predicted result, calculated result. So this is the discrete state space, and as you can see, this V by 25 is a damping that kind of simulate the air drag as well as the friction drag from the floor when there's no input. It try to reduce the velocity to zero, basically regulate the velocity. So these are the state Jacobian for the state space in terms of with respect to states as well as input. So I use these two matrices, these two functions in my optimization. So output is a full state, but it has some noises. I scale these noises appropriately to match with these scales. These are X and Y varies from 1 to 50, 60. So this W and W2 varies from 1, 0 to 10. And psi k is within 0 to pi by 3. Sorry, pi that means 3.1. So this W2 actually varies within 0 to 1. And VK is also similar 0 to 10, 0 to 1, because VK only varies within 5 to 0 to 5 range. So my controller, I use a nonlinear model predictive controller, which uses quadratic cost function. And this is the standard cost function. I don't define my own cost function. One is I don't have a reference trajectory. I just decide controller to decide the trajectory that best suitable for the scenario. And as you can see, drives the states and the inputs towards the goal location. And so so this xh actually should be the goal current x and the goal location. So it's basically not just the x of the robot vehicle, but the error between vehicle. So my weight, I gave high weight for the x and y because I want to control the position of the vehicle a little bit. I want to keep it in safe distance and control it. And my heading angle and the velocity has a low weights. That implies I am not kind of interested in those variables. and my uh, R input, I give high weight for the acceleration and low weights for the uh, uh, steering angle. So these are the constraints. This constraint ensure that my vehicle is within the uh, lane, and this constraint is for the obstacle avoidance. It says, okay, your distance between you and your obstacle should be higher than this value. And these are for constrain the input. This is the maximum acceleration it can use, and this is the maximum steering angle it can control. This is the maximum steering rate. I use this one to stop the jerking effect, and it gives me some smooth trajectory, smooth motions. So this controller use fmin con as a constraint optimizer, and in that optimizer I use a SQG, sequential quadratic programming optimizer, to use that my Jacobian to calculate the Hessian and the Lagrangian multiplier to uh, compute the best direction to search, and it's very faster. So these are some of the results. As you can see, this is a 10-step horizon. It looks 10-step, and this is 5-step horizon. You can see 5-step horizon has some jerky effect because of the less uh, foreseen thing, I would say. So vehicle does not collide with the other vehicles, and it keep maintain its speed with the other vehicles because of the constraints, and it try to go towards this goal location. So this is two-way traffic system. You can see when vehicle waits until the other vehicle is parked so that it can overtake the vehicle. This way I just give a static position, but I can keep it going of for forward and forward, but in the to simplify the system, I consider this one. And also you can see it's in 5-step horizon, it has this jerky effect, but 10-step, it knows, okay, this thing is going forward, so I had to keep maintaining my distance. These are some other effects that I want to show, that to show the robustness of the system. As you can see, it in 5-step horizon, it park the vehicle without any issue when there's other systems. And 9-step horizon, yeah, it's more smoother. It takes the turn a little bit before than the vehicle, as you can see. However, when the step horizon is 10, it gives me this weird result. This is, I believe, because of my Jacobian may be at ill condition, and it result a bad Hessian matrix and Lagrangian, which drives the search in a wrong path, and also that Jacobian is used to handle the constraint. In this case, yeah, it clearly violates the constraint. It goes away from the boundary. So, however, it's little, I'm confused that only 9-step horizon works, but 10-step horizon doesn't work. So these are different scenarios to show the performance. This is the same MPC controller, the same cost, same constraint, only the goal state is different. As you can see, it parks, you can park in any angle, parallel or vertical parking. So this is to show how controller works when there's a sudden object appears. It figure out there's a sudden object and take a sudden turn to avoid that object. This is actually kind of cool to see. So this is another way to show that the controller robustness. This is the goal location, but it realized that it can't go beyond this point, so it stopped the car and keep the distance. It doesn't. It seems like it collides the system, but it doesn't actually. But yeah, that means system knows, okay, I can't go beyond this point. So what I learned, I got a better, way better than understanding than my previous knowledge about MPC. I learned how to formulate my problem to a nonlinear model predictive controller, and what happens in nonlinear in model predictive controller, and the optimization, how it works. And I realized that, okay, a bad model can give you bad results, especially this ill condition, as I demonstrated before. Also, I realized that the parameters are very important when it comes to a controller. You have to figure out proper parameters so that it gives you the correct value. So I had to tune the weights, because if I give same weights through the system, yeah, it gives me in wrong result, and it gives you very jerky path because you try to control the direction as well as velocity. So also I learned how to derive uh, my own simulation in MATLAB and how to write an MPC controller without using a simulate model or something, just coded on the MATLAB, which gives me good understanding, in-depth understanding about the control and how to add my own constraints, my own constant functions, cost functions and stuff. As a conclusion, my main conclusion is MPC is very robust, it's very powerful. I developed this controller with a simple cost, and I have some real world emulations like damping as well as these noises, but still model predictive controller managed to give me good result for various different scenarios. It's true that I don't use a dynamic model, which might give me a hard time, but model predictive control is very powerful as long as you tune the parameters and formulate the system in a quadratic fashion, and it gives you the best result that it can give. So thank you so much for listening, and these are the reference that I used, and these are the most of the reference in my report as well. Thank you.